see the first slide. I have here both English and Czech name of the method, but well, there's magnetic particle imaging is official name of this method, but it's pretty new and still there is no Czech name. Probably we can translate it like zobrazování magnetických částic, but as there is only one scanner in the Czech Republic, and moreover the scanner is not in good shape, so the method is really pretty unknown. So probably even for you it will be quite a new thing. So starting with some history. First MPI image was presented about 20 years ago. In 2005 was published paper in Nature, which presented a novel tomographic method for imaging using magnetic particles. In 2008, the same group presented experimental results and some theory and practical approach how to measure spatially resolved images in real time, not only the principle but usable method. So, magnetic particle imaging belongs among non-invasive imaging techniques. It doesn't use ionizing radiation, but it requires a tracer. It provides no native image, so there's no anatomical information in the images. Therefore, it requires colocalization with another imaging method like X-ray, CT, or MRI. MRI might be useful because it might use also the same nanoparticles which are used as a tracer, and they produce contrast in MRI too. So it might be pretty interesting combination of magnetic particle imaging and magnetic resonance imaging. And the tracer for this novel method is based on superparamagnetic nanoparticles. So I'm just shortly remind you, I already showed you these pictures, what's the difference between paramagnetism, ferromagnetism, and superparamagnetism. For this lecture, it will be really very important to understand what superparamagnetism means. So, paramagnetic material, we can imagine that it's consisted of a lot of small dipoles which are randomly oriented in a zero field. But if we switch on external field, they start to reorient along the magnetic field. And of course, at strong magnetic field, all dipoles are oriented in the same direction, and we measure maximum of magnetization. And if we further increase external magnetic field, there will be no change of magnetization, of course, because all the dipoles are already oriented. If we switch off the magnetic field, the particles, the dipoles again become randomly oriented and magnetization becomes zero. Ferromagnetism is similar, but once we magnetize the material, bonds are created among the dipoles, and it keeps its magnetization. So even if we switch off the magnetic field, there will be non-zero magnetization. We can turn it around by strong magnetic field oriented in the opposite direction, but we will never get back to the 0 point. So, but this material is, of course, this property, of course, depends on temperature. If we heat the material, of course, due to thermal energy, these bonds are disrupted and the material becomes again paramagnetic. The temperature at which this happens is called Curie temperature. And for example, for iron, this temperature is around 500 to 700 degrees Celsius, so it's very high. But there are also materials which with much lower Curie temperature, and of course materials which are paramagnetic at normal temperature have Curie temperature somewhere very low. So superparamagnetism combines both these effects. You can imagine that they consist of ferromagnetic crystals or particles, but they are very small so that the whole particle can rotate. So in the magnetic field, whole particles are oriented in this in the direction of the magnetic field, which of course means that the response to the magnetic field is very steep. So we should distinguish two processes. Either the whole particle rotates, we call this Brownian rotation in the external magnetic field, or only the whole dipole inside the particles may be reoriented. And we call this process as Néel's rotation. And both these effects we can observe put together superparamagnetic properties. So what's the principle of magnetic particle imaging? So as I mentioned before, superparamagnetic in a magnetic field follows this curve. In fact, this can be described mathematically using a Langevin equation, which is here, and and the nanoparticles respond to the external field by alignment, and both processes, Néel's relaxation and Brownian relaxation, take part. So I will get back to the Langevin equation a little bit later. And now we will look what happens if we apply alternating field. So if we have magnetic field B, which alternates, which changes in time like this, we can induce reorientation of the nanoparticles, and they are going up and down along this curve. So the magnetization changes like this. In magnetic particle imaging, we call this alternating field, which excites, in fact, the nanoparticles, like dry field. So, if there's no other magnetic field, we have only the dry field, we can induce change of magnetization like this. But if there's a static external magnetic field, which saturates the nanoparticles, so there's already maximum magnetization, and we switch on the alternating drive field, then we see no signal from magnetization because the particles are already saturated and we are moving back and forth in this part of the curve. So they are at the minimum drive field, and then the maximum drive field, they are still saturated. So only at zero field, I can see the response of the magnetization. If there is an external field, static field, I cannot see any change of magnetization. And this is important for spatial resolution in magnetic particle imaging. So now imagine that we have external static field which has a gradient, so it changes in the space. We can create it by two magnets which are have opposite direction, so that there's gradients along these lines, and in the middle there's a point where the field is zero, where the contribution from one magnet and the second one just cancels. So here is zero magnetic field, but the magnetic field from this point increases towards the border of the space limited by these two magnets. So in the middle, if we now use the drive field, in the middle we can see change of magnetization with the same frequency as is the frequency of the drive field. But if we look at other positions, here, here, or here, where the field is non-zero, from these points, I receive no signal. If I apply the drive field, the particles are already saturated and I see there no signal. So the change of magnetization induced by the drive field is observed only from this small region in the center. The rest of the particles are saturated and provide no signal. So this is the basic principle, because we can now scan by the field-free point whole space, placing a field-free point here, then here, do the scanning and so on, and check whether we obtain their signal, which means there are some nanoparticles, or if we don't receive any signal, it means there are no nanoparticles. So I could scan the space like this, point by point, and from each point measure the spectrum and check whether the nanoparticles are present there or not, and from this put together a whole image of distribution of nanoparticles in the space. However, there is a lot of problems. First, it's a physical problem because we need to measure magnetization, acquire the signal during excitation. So the drive field is on, and at the same time, I'm measuring the same frequency of changing magnetization. This is a very big problem. Then there are technical problems, of course, whether we are even able to build an equipment with sufficient field strength, both for drive field or the gradient static field. Practical problem is that sequential scanning of a 3D space, as I showed you on the previous slide, would be very long. Scanning just point by point in 3D space takes really a lot of time. And then, of course, we need some superparamagnetic particles with special properties. They should have good physical properties, but also they should be non-toxic, biocompatible, etc. So there's really a lot of problems connected to this method. So what can we do with the acquisition during excitation? Hint is that we need amplitude of the alternating drive field big enough to cover not only the linear part of the Langevin function, but it should reach also the nonlinear part of the magnetization curve. If we measure only linear part, then magnetization will follow sinus, and this will be a problem. But if we cover also nonlinear part, then there will be contribution, the curve would not be the sinus, simple sinus, but it will contain also higher harmonics. In fact, what we measure is the change of magnetization, so derivative of, or rather, sorry, integral intensity. But if we take this signal in time and look at the frequencies, which means perform a Fourier transform to see all the frequencies which are available here, then we obtain signal spectrum, which contains, of course, the basic frequency, which corresponds to the frequency of excitation, and the sinus frequency here. But because this is not exactly the sinus, then there are also higher harmonics available. Of course, the first frequency, which corresponds to the drive field, contains contribution mainly from the drive field. But if we have signal spectrum like this, we can just simply filter this frequency, and for evaluation of the signal, use only the higher harmonics. So this is the method. How can I get rid of the problem that we acquire the signal during excitation? Because the signal from the excitation field I can filter out. The condition is that amplitude should be big enough to cover also non-linear part of this curve. So the second problem I mentioned was how to gain spatially resolved data. There are two approaches. One uses field-free point method. This is what I outlined before, that there's a gradient field and only in one point the field is zero. Or another possibility is to use field-free line approach when the magnetic field is zero along one line in the space. So I'll start with the field-free point approach first. It's a little bit complicated, but it's pretty interesting. I can apply drive field from different directions at once. So I will use 3 drive fields with from 3 orthogonal directions. And I can imagine that one field excites the particles, while the other 2 are moving the field-free point, because at the beginning with the gradients, I have field-free point in the middle. And if I apply alternating field, it means also I can imagine that this field-free point is moving back and forth in one direction. Again, and if I apply it from different directions, the field free point moves through the whole space. Something like this. Of course, the space in which the field free point moves is given by two factors. One is the strength of the gradient field, the static field, and by amplitude of the derived field. If I want to cover wall volume, then I need a higher amplitude, of course. So, what in fact happens with the field free point if I apply alternating fields from different directions? First, look what happens if I use 2 dimensions only, so 2 fields with the same frequency and same phase. And if I apply it, then the 0 point will move along this line. If I change the phase, so this field starts at -1, this at 0, then the field free point will move in the circle. If I have different frequency of these fields here, here is the basic frequency, and here is the frequency 2 times higher, then the field free point will move along this curve. These curves are called Lissajous trajectories, and of course, their shape depends on the phase. So if it is a sinus, the phase is this delta between these 2 fields, and also on A and B constants, which change the frequency of the sinus. Here is another example. So again, from same frequencies with different amplitude, with different phase. Again, same frequencies, and here in the lower row are different frequencies: 1 and 2, 2 and 3, 3 and 4, and so on. I can continue with this further on, and you can see that with values like 4 and 11, I already have pretty dense curve through the space, or through this 2D image. I mentioned before that I use 3 derived fields, so the same I can do for 3D. The curve will be much complicated. Again, there will be 3 parameters defining the frequency, and parameters defining the phase, delta 1 and delta 2. So current technical possibilities which are available at our machine have these values of gradient selection field, alternating derived field, this is the amplitude, but what I want to speak now about is mainly the frequency. The frequency is approximately 25 kilohertz, but it's derived from the virtual basic frequency 2.5 megahertz, and the frequencies in 3 directions are derived as these ratios. So they are pretty close, and the closer they are together, the more dense net of the Lissajous trajectory I can obtain. So therefore it's f over 96, f over 99, and f over 102. So the frequency is approximately 25 kilohertz, and whole trajectory repeats every 21 milliseconds. So the scanning of the whole space is very fast. Here you can see how dense is the net in 2D. So this is the 2D trajectory for two two directions of the drive field. And if we use 3D drive field in 3 directions, it looks something like this. I already mentioned before that the scanning volume is given by the amplitude of the drive field and by the strength of the selection gradient field. Altogether, our machine enables maximum usable volume, something like this, 48 millimeters times 33 times 24. And it's a pretty small volume. It's almost not enough for a mouse. So there are some possibilities how to enlarge it. Of course, we can lower the gradients and use higher drive field amplitude, which would increase the volume, but we should be aware of the fact that this would decrease spatial resolution. Problem is that we have the same Lissajous trajectory. We cannot change this because it's given by the frequency. And if we increase the volume, then the trajectory becomes less dense. So I obtain the same number of points here, same absolute resolution, but not the same spatial resolution. So in fact, the spatial resolution decreases because I still have the same Lissajous trajectory, which defines the density of the data. So I will get back to the problem of the volume later, and now we can have a look on how to decode the signal. This is pretty complicated. We have a sample in the space. We can measure along the Lissajous trajectory some signal, and how to decode this. In practice, we need to perform a calibration. So we take a sample, which we know how is concentrated and how is big. Usually we use a sample which corresponds to the voxel in the space defined by the machine. And step by step, we measure the signal from each position in the space. So we know its concentration, we know how is it big, and we know which signal it produces when we place it here, here, etc. So we measure calibration data for every point in the space. It takes really a lot of time. Usually we measure this overnight. It takes 10 or 20 hours, but we need to do this only once for the given tracer. Once we have this calibration data and we measure an unknown sample, for example, mouse with injected tracer, we obtain signal like this. And what we do now, We already know that this signal contains, as it was measured along the whole Lissajous trajectory, we know that it contains information from the whole volume. So we fit this signal by the single calibration data, which we already measured, and find linear combination of all these calibration data. And from the linear coefficients, which we calculate from the fitting, we can put together concentration map of the unknown sample. What is necessary to remind here, the sample has to contain same particles for which we made the calibration. So we do once the calibration for one particular tracer, and then we can use it. And the scanning of all the mice with applied tracer takes just tens of milliseconds. It's very fast. Only the calibration takes many hours, but it needs to be done for the tracer only once. And we can use it all the time. Of course, if we change the particles, which might have different response to the magnetic field, we need to redo the calibration. It's a question whether it's possible to decode the signal directly, and so far there's no method how to do this, and probably it might be possible, but probably the result might be ambiguous. So still the approach with the calibration and making linear combination of the calibrated data to the measured unknown signal is so far the only working approach which is available. Here are the data from the calibration. They are quite strange, but you can imagine that it's really a lot of data. We obtain a signal from each point in the space. The signal contains information from several harmonics, so whole spectrum. So the data which the calibration produces usually contains files with gigabyte of data. Here are different imaging of different harmonics, first, third, fifth, and so on. Much more simple is field-free line approach. This is the field-free point when we have signal only from the center, but the field-free line has zero field along one line, while everywhere else is strong magnetic field. One big advantage is that it's more sensitive, because during single scan I always obtain signal from whole line, not from one point, and it's much easier to reconstruct the data using a radon transformation. You already heard about radon transformation in the case of computed tomography. So probably you already saw these equations. This is signal distribution in XY plane. Signal along a straight line can be calculated like this integral. We can calculate this. You don't need to know all these calculations. But hint is that the signal is always along the whole line, and then we can calculate inverse radon transformation. But of course, we need to fill the radon space by measurements at various angles along which we use for integration here. So we need to repeat this, rotate with the field free line in the space, measure the signal along each line, and then we can calculate the distribution of the density of the tracer in XY plane. One very important thing is in this method the question of the contrast agents. Here, the case of nanoparticles. I already mentioned that we need superparamagnetic particles. I already told you what it means. Usually, these particles are formed by iron oxide cores, which are coated by some kind of a sugar or polymer, or, for example, silica can be used. But what we should remember is that physical properties of these nanoparticles define image quality too. Even spatial resolution is dependent on the type of nanoparticles we use. I already spoke about gradients, selection field, which of course defines resolution, but also the type of the nanoparticles. This is given by this equation, which shows magnetization in the presence of magnetic field. This is the Langevin function. Here you have the prescription for it. But if you look at this image, you can see that the size of the particles define how steep the curve will be. This is given by the effect of mu, because the core size is related to magnetic moment. So if we use small particles, then it will be very hard to reach nonlinear part and to get more higher harmonics here. Therefore, the resolution will be much worse than in the case of big particles, where the signal, the change of the magnetization is very steep. So the bigger the particles, the higher resolution I can reach. Of course, the best thing would be to have particles with this shape of Langevin function, but of course it's clear that it's not possible. Here is a table of theoretical resolution which we can reach with different diameters of the nanoparticles, and you can see that 10 nanometers, well, a resolution of 21 millimeters is really very bad, so we should go down here. In fact, this is not exactly valid in practice, because in real life we can reach higher resolution by detection of higher harmonics. So I don't need to take only these harmonics in the spectra, but I can use also the others, and using these values I can improve the spatial resolution. The second important property of the nanoparticles is relaxation. reorientation of the nanoparticles in the magnetic field is a dynamic process, and also the speed of the response is very important. Of course, it's clear if the response will be very slow, so the particles might not react to the quick changes of the alternating drive field. So it's necessary that the relaxation processes are fast enough so that the particles can follow the alternating drive field. Change of the magnetization, I already mentioned this, is given by Néel's rotation. This is change of magnetization due to reorientation of the inner magnetization. And by Brownian rotation, which means that the whole particle rotates in the space. So here is another picture. Brownian rotation, we rotate the whole particle, while in Néel's rotation, I rotate only the magnetic moment of the nanoparticle. Néel rotation is characterized by a relaxation time, of course. It can be calculated like this. Tau 0 corresponds to the frequency of geomagnetic rotation, so it's exponentially depends on temperature, of course, on the volume. And similarly, Brownian rotation can be calculated like this. This is viscosity of the environment. Again, here is the volume of the particles and temperature. You should remember that both relaxation processes are involved in reorientation, and that Néel's rotation is usually much faster than the Brownian rotation, but it depends on the volume. Again, I should remind this to you. And both equations show that the size and shape of the particles is very important. We can calculate efficient relaxation time. It will be combination of both, it's clear. Also, it's quite interesting that small particles will exhibit most likely Néel's rotation, while large particles will be dominated by Brownian rotation due to so-called block Néel's rotation. If the particles are too big, then it's very hard to rotate only the magnetization inside the crystal structure. So small particles exhibit Néel's rotation, large should be rotated as a whole. The question is why to bother with relaxation? Why not just to slow down the acquisition in the sample? If we lower the frequency of the alternating drive field, then the particles, even with slow relaxation, can follow these changes. But the problem is, well, here is the equation for the signal which we can measure. It's pretty complicated, but what's important here in the integer is the derivative of magnetization, and this is very important. Because if I do some calculations here, I can at the external homogeneous field obtain equation like this, which means that the signal depends on the time change of magnetization. And of course, if there is slow change of the alternating magnetic field of the excitation drive field, then there will be slow change in the magnetization, and slow change in the magnetization means very low signal. So to obtain signal which is measurable, I need to have high frequency of or fast changes of the alternating dry field. Therefore, the relaxation processes are important for us, and it's not possible just to slow down the acquisition. So, I already showed you that size of the particles is very important. I need particles which are big enough for good spatial resolution, but small enough for reasonably fast particle relaxation. Luckily, these limitations roughly delineate an interval corresponding to particles which are already used in biomedicine. Of course, the size of the particles should be taken into account from the point of view of toxicity and biocompatibility. So we need particles with the size around 30 nanometers, which is still okay to from the biological point of view. Of course, as different particles have different response to the magnetic field, it's very important to have narrow size distribution. This would not be good. So all the particles, if it is possible, should be uniformly sized. Here is an example. This is a standard commercially available crystal, and here are two types of nanoparticles with broad distribution of sizes and narrow distribution of sizes. And you can see that the resolution, of course, is much better if the particles have narrow distribution. The machine itself looks like this, but I'm sorry, when you come to our lab, you won't see it because it's broken now, and due to COVID and impossibility to travel abroad, the guys from the service company cannot come to repair it. So now it's per partes in the room, but well, it's alive. The machine itself is pretty complicated. Here inside is the magnet which creates the gradient field together with coils producing alternating dry field. Here in the back, looking through this window, you can see it here, is a robot which enables placing a rod with the sample and moving it back and forth, up and down, left to right for calibration. So here we place a small test tube with exactly defined size with the sample of nanoparticles, and this robot moves the sample in the magnet and scan the space for the calibration. As I mentioned before, calibration takes many hours, but once the calibration is finished, then the scanning itself is very fast. It takes 20 milliseconds, so it enables also nicely temporarily resoluted information. Here, so far, we haven't performed any in vivo experiments. So here is an image of a phantom. These holes filled with a tracer are 1 millimeter apart, you can see that we were not able to reach 1 millimeter resolution. But again, it depends on the calibration data and on the setting of the instrument. As I mentioned before, it enables 3D reconstruction. We obtain the data from 3 dimensions. The same phantom, you can then look at the sample from different directions and rotate it as you want. Scanning volume is pretty small, as I mentioned before. So how can we increase it? We can make use of the fast scanning. So if we need to scan bigger volume, we can enlarge the field of view by 2 approaches. First is using another magnetic field, so-called focus field, which shifts the whole field of view in the space, just moves the basic field-free point in different directions, so you can sequentially scan the whole volume. Here is an example. This is a phantom in the shape of a rat, and here it was scanned in 3 parts and put together. Another possibility is so-called table move approach, when we don't shift the field-free point or the magnetic field, but we simply shift the sample in the magnet and measure a sequence of images and match it into one. Here is again an example of the same phantom, 3 images put together using this software. First, this was the first carriage for the sample. We used it from Lego to move it back and forth in the magnet. Then we printed out a holder for rats and mice, which might be used for in vivo imaging. So in one direction, we can easily shift this and perform sequential scanning in the space. Although the method is pretty new, there are still different ideas what it could be good for. It's even possible to do a temperature mapping using this method. You probably remember that the signal depends on temperature, so you can change the frequency, and the frequency defines from which type of particles or from which temperature you can obtain the signal. So temperature mapping is possible. There are also approaches to use it directly in certain pathologies. Here is first in vivo traumatic brain injury using this method and so on. So it's still under investigation what this method enables in near future. So to conclude, magnetic particle imaging is potentially a very interesting imaging method. Also, all the possibilities are not completely appreciated yet. What you should remember, it requires a contrast agent which is based on magnetic nanoparticles, and we image only the tracer. It provides no anatomical information. Therefore, it requires a colocalization with another imaging methods, method like MRI or CT. So far, it's rather an area for research than as a usable preclinical method. The areas in which research is underway are related to data acquisition and processing. As you already saw, data acquisition is very complicated and processing is not simple. Then there is a lot of space for development of nanoparticles which would better respond to the magnetic field. And so far there's not too many applications, so still it's under investigation what it would be good for. There are also ideas that it might be used both for imaging and, for example, for thermoablations using the same nanoparticles, because at high frequency alternating field, now I mean megahertz, these particles can heat themselves in the magnetic field, so it might be possible to use the same particles for diagnostics and for thermoablation. So that's all for today.